I think we should start the opening session of that Pvcon 2020. Dear our guests, invited speakers, oral and poster participants, many thanks to you all for joining Pvcon 2020, second international conference on photovoltaic science and technologies, a virtual online conference platform organized by Center for Solar Energy Research and Application, namely GÜNAM, in Middle East Technical University of Ankara, Turkey. We would like to start by giving again to you all our sincere thanks to be on this platform to join and present your researches and applications. Welcome to you all. First of all, we should think that such occasions are extremely important on widening and heightening of our social assemblies. This conference and similar of others are very important overall, but the time now we are involved is an exceptional situation, which is happening, but hoping on one side, this makes us to believe and extend unification of our goal. The situation now all over the world forces us firstly to live and secondly to study and meet. Developed and developing countries seem all heavily affording to win against COVID-19 and hoping that we will reach soon better and healthy days. We keenly wish our patients to become healthy and join us, and we give our deep gratitude to healthcare providers, helping and working staff members, and those all working against coronavirus. Now, if we come to Pvcon, after the success of Pvcon 2018, we would like to organize second Pvcon 2020, and now, although remotely for the time, but we are together again. That is the scientific people working on PV research and technologies. We do hope that the present organization will again be successful and open new scientific and technological cooperation on the way of having a better world for us. Another hope for us, in such international conferences, we are adding invaluable efforts with scientific collaborations to reach a better Earth, for her to continue to be a home for us without pollution and without global warming. Coming to solar PV side of the research and technology, now the PV plants are quite larger than 600 gigawatts all over the world by the end of 2019. And it is increasing with higher rates, and probably it will be over 700 gigawatt by the end of this year. What about the largest power plants? The largest PV power plant is now Badla, the largest solar park in India with 2,245 megawatts, 2.245 gigawatts. And he surpassed China's largest 1,547 megawatt of Tanji, Inner Mongolia. And also India's second solar park of Pavagado Taluk is about 2,050 megawatts. It's 2.05 gigawatts. As can be seen, India PV is increasing rapidly. As of 2019, he was in the 5th, but nowadays, or the next year, he will be the 3rd after China and USA. China at the end of 2019 had 205 gigawatt PV power plants, which is about 33% of the total plants of the world, while USA was about 76 gigawatt with 12%. By the end of the year or the beginning of the next, these figures may slightly change. If we come to Turkey, in fact, in Turkey, we are also working and installing more and more utility scale plants, while legislations for the rooftop modular system are stated, amendments declared, and installations are already started. Now, Turkey has already quite more than 6 gigawatt solar power plant installed, almost in all around Turkey's land areas. This number, 6 gigawatt from a few months before, now it should be around 6.5 gigawatt. Turkey is the 13th country of having PV investments. There are more than 25 companies producing PV modules, 2 large companies producing the solar cells, starting from wafer, and one of them already started to produce silicon ingots and obtain silicon wafers. This company is already investing a 1 gigawatt power plant to be implanted in Middle Anatolia. It will be finished in a year or so. The work for this installment is already started. One of our keynote speakers of this session is from this company. With these figures, we can firmly state that it will continue in the coming years, and PV electrification will heavily increase all over the world. Africa countries will come in turn with their huge land areas, continue to cover the surface with more and more solar PV modules. We should also note that the solar potential seems the largest of all other renewables. The solar potential is the largest of all the other renewables. Another issue that we should underline is the next generation solar cells. There are many laboratories and research centers are working on these topics. There are many different types, and some of them are very close to be in the market. Some of researchers aim to produce multi-junction solar cells of very high efficiencies that can take place apart to be used in different applications of solar PV. That is, it seems that in the new solar PV installations, these new generation cells with their higher efficiencies will take their place in many investments and applications. Soon, we will be wearing high-tech suits, receiving the light, and continually charging our phones and tablets while we are doing our jobs, supporting or resting in our houses. As a final word, we should keep going toward a greener and healthier Earth. Now, I will leave the talk to my friend Rashid. He will give a short presentation about UNAM, that is our place of scientific research and application platform. Rashid will take the stage.
Okay, thank you very much for this nice introduction and nice opening speech. First of all, I would like to welcome all of you to our second Pvcon conference. We hope to do this face-to-face here in Ankara. We plan to do this conference in July, but unfortunately due to the COVID virus problem, we had to postpone it to this date, and we hoped to do this again face-to-face in this date, but unfortunately the virus is now becoming worse and worse, and we have to do this online. Taking this opportunity, I would like to give you some information about our activities at UNAM in Turkey, and I will be very brief. Just let me share I have a short presentation, share this presentation with you. I hope you all see my presentation. UNAM is now becoming a regional European and global research hub on solar energy conversion technologies. It is located in Ankara, in the beautiful campus of Middle East Technical University. And we have a short history, actually. We started in 2009. We are almost 12 years old. However, the first paper on solar cell research was published in 1986 from this university, from Middle East Technical University. We founded UNAM in the beginning of 2009, and then we have invested to set up an infrastructure, mainly to fabricate photovoltaic systems, photovoltaic solar cells, modules, etc. Also, we have a group working on solar thermal energy, which is very active, especially in the European projects. So we have reached a lot of milestones. We have reached a lot of achievements during these 12 years, and we are proud of this. And then we have done many projects, many European projects, national projects, a lot of activities, including this one. And then we have now come to a new stage, which is, we call it Metrologist or new Metrologist. A new status has been now authorized to us under the law of numbers 6550. Now Metrologist has been recognized as the Turkish National Center on Solar Energy Technology. This is a kind of recognition by the state. So the new Metrologist we will be a new legal entity independent from the universities. We will have our own budget and own personnel structure. we will have a kind of autonomous management with operational independence. This decision has been made very recently, just a few days ago, and we have now started to work under this new legal structure. Okay, the structure of new GUNAM is shown here. Apart from the management structure, we have 6 major divisions. These 6 major divisions are shown here. Silicon photovoltaics is maybe the major one because it has the closest interaction with the industry of the country. And also emerging photovoltaics, module technologies, power electronics, system integration, concentrated solar thermal energy, test and characterizations. These will be our 6 major divisions. And depending on the needs of the country or the community, PV community, we will make necessary adjustment during this initial stage. Okay, here are some pictures from our divisions. Silicon photovoltaics maybe is the strongest one with highest number of people working and largest infrastructure. And also emerging photovoltaics is very productive unit in our center. Module technologies is starting now. Actually, we have a very good outdoor test platform under this group. In this group, power electronics group is also starting up with equipped laboratories and also people. And solar thermal power is operating together with mechanical engineering department of the university, and we have a strong test and characterization unit. Okay, we will have 2 major buildings, 2 major facilities. One of them will be in the so-called Metrologist Research Park building. Here we will have a new clean room with 500 square meter active area, laboratory space area. And this part will be connected to the other research centers at Metro. The other one is a unique R&D based structure, which is a kind of pilot scale production line. In this facility, this is fully operational now. We can fabricate all standard silicon solar cells, including PERC, aluminum BSF, bifacial, IBC, etc. So this facility is open to industrial research. It's more oriented towards the industrial research, and we hope to have more collaboration with the companies and industry in Turkey as well as in the whole world. Okay, this picture is showing the inside of this facility. As you see, we have an infrastructure which is compatible with the industry, but it's flexible enough to do R&D research activities. Another very important initiative we have taken very recently is to set up a new platform in Turkey, which is called Turkish Photovoltaic Technologies Platform. This platform will be supported by the government, by TUBITAK, which is the major funding agency in Turkey. In this platform, we will have industry as well as some other universities. Currently, we have 9 members of the platform, and these 9 members will be focusing on PV cell technologies, mainly silicon, module technologies, and PV power electronics. We do have also some international partners here. Fraunhofer, ISE, and IMEC are two partners now joining us in this platform, but we will have more to join in the coming years. So this platform will have financial support to do some projects. Okay, with this short introduction to GUNAM, I would like to welcome you again, and I hope and I wish you have a successful, useful, and fruitful Pvcon conference. Thank you very much.
Many thanks. This very nice introduction of our research and technology platform, GUNAM. And we will be moving a new stage. And with this new stage, I believe that everything will be better and better from the PV solar side, I hope. Now, the next speaker, actually, our first speaker is Ron. Ron Sinton did his PhD work at Stanford University, developing 28% efficient silicon concentrator cells and 23% efficient backside contact one-sun cells. He then continued to be more industrial as a founding member of Sun Power Corporation, Sinton Instrument, in 1992, working on device physics approach to develop very high efficiency silicon solar cells. He was involved in the development of many techniques that are commonly used today, such as the Suns-Voc techniques and the methodology for extracting and reporting implied voltage from lifetime data. Sinton Instruments provides metrology for nearly all of the research labs and production facilities working in silicon PV technology. He works on the boundaries between metrology and device physics to report parameters with physical models. Ron received the Cherry Award at 2014 IEEE PVFE. And Ron, please, Ron will take the stage.
I am here, but I believe that they're going to play a pre-recorded version.
Yes, Ron, it's about to be ready.
Okay, good.
Yes, Ron, it will start.
Hi, I'm Ron Sinton from Sinton Instruments in Boulder, Colorado, USA. I'm very pleased to have the opportunity to participate in this conference and talk about carrier recombination lifetime. Our company does metrology, and we specialize in lifetime measurements of the minority carrier lifetime in silicon for photovoltaics. And this is because this is a critical parameter for PV all the way from the beginning of the process, as soon as the material is crystallized, right to the end for the field installations. And in the beginning of the process, you can qualify your material for material quality, for purity, for crystalline quality. During the process, you can monitor your wafer lifetime to see if you've had a contamination event, or to optimize your passivations and make sure that process control is under control. At IV test, you can measure the entire characteristic of the solar cell and basically know what your process control was in the line after all of the high temperature steps. And then we have module testers as well that can qualify the modules right before they're sold. So carrier lifetime is a unifying feature in the PV value chain all the way from beginning to end. In addition to these features, at the IV test, you can do energy loss calculations and figure out how to re-optimize your solar cell design or process. I'm going to talk a little bit about solar cell and module degradation mechanisms because lifetime is a very good way to study these as well. There are three main ones: LID, light-induced degradation, which is boron-oxygen pairs; LETID, light and elevated temperature-induced degradation; and then the loss of surface passivation with field exposure. So first, we'll talk about lifetime from first principles. What we're talking about is the lifetime of an excess electron hole pair in silicon. And this is usually determined using the continuity equation, which was in even the first textbooks on semiconductors by Shockley. And the lifetime of the electron hole pair is equal to the carrier density in the wafer divided by the photo generation minus the carrier density as it changes with time. In the steady state, it's just the carriers per unit photo generation, and this is what it would be in a cell or a module being used. And in a lifetime test under transient conditions, it's the carrier density over the change with respect to time of the carrier density. So what we can see from this equation is that what you need to measure to determine lifetime is the carrier density as a function of time. And you can do this with a number of sensors, and people do. One of our favorites is the eddy current sensing of conductance, and then you convert to carrier density using mobility. You can use luminescence from excess carriers, EL and PL, and this is just looking at the NP product in the cell. IR absorption, the free carrier absorption of free carriers, tells you how many there are in the cell. And finally, after IV test, you can use the diode voltage under open circuit conditions. In this talk, we'll be talking mostly about eddy current sensing of conductance and using the diode voltage. Now, the first and the most common application for lifetime testing is in the process line optimizing the bulk lifetime and the surface passivation. And this is often done with a wafer that has surface passivation on the front and the rear. It's measured on a lifetime tester. And when you take 1 over the measured lifetime, you can separate that into 1 over the bulk lifetime plus the J0 with a constant, which depends on the carrier density delta N, the excess carrier density. So this is the slope. If you take the slope and correct by a constant, that gives you the J0 of the surface, and the intercept at the negative doping gives you the bulk lifetime. This is an analysis that you can do on most N-type wafers, especially undoped or lightly doped N-type wafers, and it's the most common application of lifetime testing. Now, just to generalize this a little, you can do the lifetime versus injection level as a function of temperature. And this gives you access to much more fundamental parameters. There's a lot of research, especially in the last 20 years or so, with actually identifying the trap level and the ratio of capture cross sections in order to get a fingerprint for various defects like iron or chromium in silicon, boron oxygen defect, and these other things. And by using temperature, you can get a much less ambiguous determination of these parameters. And I'm not going to go into detail of this. It's better done by others, and if you want, I can give you references. But I will mention some of the applications for the degradation mechanisms, and I'll just use the LET ID in PERC structures as an example. And when you have your finished solar cell, you might find that it has a 75 microsecond lifetime. But then if you heat it up to 75 degrees C and soak it for some time, 24 hours at one sun, you'll find that the temperature, that the lifetime drops to 18 microseconds in this specific case. And if you look at it on long time schedules, you can see that at 95 degrees in VOC, the voltage will drop precipitously for about 200 hours, and then it actually starts to recover. And at more moderate temperatures, you stay in the degradation phase for a very long time. And also under ISC mode or VMP mode, you would see this effect. So this is a serious issue with modules, or it was in about middle of the last decade before it was solved. And the leading hypothesis is that this is caused by excess hydrogen in the silicon, as well as some other aspects. And there's a demonstrated process fix for this, which is just to control your firing temperature, and in order to get just the right amount of hydrogen in the silicon. And there are other tricks that can be done, but the way to qualify these tricks and understand them in a fundamental way is often done with lifetime testing. So for the rest of the talk, I'm going to switch to determining the lifetime parameters at the IV stage, where you're using voltage as the sensor of carrier density. And so we're going to use a sample of 350 heterojunction cells in many of these slides to follow. And here we have the IV curve, current versus voltage, and the blue curve is the IV curve. And from this curve, you can determine things, all of the usual things like efficiency, open circuit voltage, fill factor. You might also get a yield curve showing how tight your distribution is. But we go a little farther than that with IV testing, and this is shown by the red curve, which is the Suns-Voc curve. And this is constructed by measuring the open circuit voltage as a function of light intensity, and then displaying it this way, where the distance between these two curves is the series resistance. So the Suns-Voc curve has all of the recombination aspects of the solar cell, but none of the series resistance. And so it's a good vehicle for really doing your fundamental device physics on your solar cell. And so using this Suns-Voc curve, you can report a whole bunch of other parameters. You can report, for example, pseudo-efficiency, pseudo-fill factor, the series resistance, as I showed you in the last slide, capacitance. But you can also do this lifetime measurement, because it's the same as the eddy current lifetime measurement, except you're using voltage as your sensor. And so we have 1/tau versus carrier density, and you can determine the J0 of the surface independently from the bulk. And so you can report the J0 surface, the bulk lifetime. And at IV test, you can also report the doping of the substrate, which is very important for the device physics. And surprisingly, you can even measure the thickness electronically from the data. And so you also get the lifetime as a function of carrier density over the entire range that's useful for IV curves. Now the end goal is to be able to make decisions. And so what we do is we use all these parameters to do a power loss analysis. And I'll describe this in more detail later, but in this case, we can see that we have 7% loss in power relative to the Auger limit due to total recombination. And we can split that into bulk recombination, surface recombination, as well as report the series resistance very precisely. So back to the beginning, I'm going to kind of tie all these things together, the lifetime and the IV curves. And to do that, I'll go back to what Dick Swanson taught me in his research group almost 40 years ago. And it's a very simple model that is very general and useful. I've found it to be extremely good. And this is that at VOC, the photogeneration equals the recombination. And so you get your maximum carrier density at open circuit voltage because the solar cell basically fills up with carriers until the recombination balances that. And so I show that in a cartoon here where red is the solar cell filling up with carriers. Now at the maximum power point, you don't want to recombine all your carriers. You want to collect about 95% of them. So you reduce the carrier density by pulling out terminal current until the carrier density is something like 5% of what it might be at open circuit. And that gives you the maximum power point. And then at short circuit current, you pull the electron hole pairs out just as fast as they're photogenerated, and you have close to a 0 carrier density. Now the voltage is just given as kT over Q times the log of the PN product. So what we can see here is that fundamentally the current is determined by carrier density because the lost current, the recombination is, and the voltage is determined by carrier density. So this is the basis for an IV curve. And so this is actually the equation for an IV curve, if you specialize in recombination anyway. And we can see that the current out of your solar cell is the short circuit current minus any shunt current that you have, and then minus the recombination. And there are 3 recombination terms. We have the bulk recombination, the surface recombination, the J0S, and the Auger recombination. I'm going to rearrange these into a diode equation. And the first thing I did is I coded some of these things red because these are parameters that you don't usually see in a diode equation. But they're the lifetime parameters, basically. You need the cell thickness, the Shockley-Reed-Hall lifetime, the surface saturation current density, the doping, the Auger lifetime, again, the thickness. And all of these are measured at IV test with the exception of the Auger lifetime. And for that, we're using the model by Richter. And so if you take this top equation and you just factor out the NP product over NI squared, then you get this. And the first term is the J0 SRH. The second term is the J0 S. The third term is the J0 Auger. And then you just have a single diode equation, e to the QV over KT. But you notice that the J0 SRH is a function of excess carrier density and lifetime, so it's not a constant. And the Auger lifetime, the Auger J0 is not a constant either. It's a function of the lifetime, the Auger lifetime, as well as the excess carrier density. So this is very convenient, this type of diode equation, in that we know that the ITRPV roadmaps actually track the J0 from the substrate and the surface as quality parameters with time. And so this is a way that you can measure it on every single solar cell as it goes through the production line and see where you are relative to your roadmap. Now, what can you do with your IV tester? I'll show you this here. And let's take some IV data, and I've focused in on the knee of the curve, the maximum power point. As you can see, it doesn't go all the way to 0, 0 here. And this is the maximum power point on the IV curve, shown in blue. This is the maximum power point on the Suns-Voc curve, shown on red. These are both measured data. Now, we can also take the Auger lifetime from the Richter study and plot the Auger IV curve here based on the measured JSC and the Auger lifetime. Now, we know that from the Suns-Voc curve, we can do this extraction of the J0. So we can take and over here I'm on power curves, we can add the recombination from the J0 to the Auger recombination, and this gives us this curve, which is Auger plus emitter recombination. And further, the Suns-Voc curve is the total J0, bulk, surface, and Auger, so we can subtract off this recombination from J0, and that will isolate the bulk recombination. So this gives us all that we have to use to get our first version of power loss analysis. And that's to look at the power lost at the operating point, the pseudo VMP, as you go from the Suns-Voc curve to the Auger limit. And you can evaluate exactly how much current is lost due to bulk recombination, how much is lost due to emitter recombination, and then you know which you should work on. And that's essentially on the IV curve, you're going from the current loss at your maximum power point up to the current on your Auger IV curve at the same pseudo VMP. And when you do this, this loss is linear in the J0. And what I mean by that is if this is your cell under test at 22 femtoamps per centimeter square, which these cells were, then as you reduce the recombination up towards the Auger limit, you go up a straight line. And when you reach the Auger limit, you're actually at the Auger limit on the Auger power curve, but not at the maximum power point at that curve. You're still at the pseudo maximum power voltage of the cell that you tested. And so this is linear recombination loss when you evaluate the power loss at a constant voltage, the VMP. Now we can do better than that. We can evaluate this power loss right up the gradient of maximum increase to the Auger limit at the maximum power point of the Auger limit. And we'll do that up this gradient slope that I show here. And I chose an easy one, which is 96% of JSC, because it nominally goes through the maximum power points because these maximum power points are all flat, and it's very easy to evaluate the equations up this line. And it's shown here. This is 95% of JMP is very close to the maximum power point on all of the equations. Now, why I chose that is that the power in an IV curve is just the current times the voltage at that point in the curve. And on this constant 96% JSC point, we have 96% of JSC is J, and the voltage is just KT over Q times the log of the other 4% over the total J0. And so if we look at how this varies with total J0, we find that you go up this blue curve and you go smoothly up to the Auger limit at the maximum power point on the Auger power curve. And this is very nonlinear. And what I mean by that, I'll give with an example. If you start with your cell under test at 22 femtoamps per centimeter square, and you reduce your recombination by 2 femtoamps, you get a modest improvement in efficiency as you go up the lines which coincide here. But if you were to do the same 2 femtoamp reduction when you're approaching the Auger limit, you get a very dramatically larger increase in the efficiency. And so it matters the order in which you reduce your various recombination mechanisms. It's very nonlinear. And so what the engineer needs to know is how to improve the cell that he or she has. And so what we give is the slope of the curve at the point where the experimental cell was, and then give the delta efficiency per femtoamp per centimeter square at the pseudo VMP here, which tells you how much improvement you can get with the next thing that you do. Now, how can we display this? We're choosing to do it this way, that the total power that's available to the solar cell at the Auger limit is the entire pi. And we're losing 10% in the various losses that we've characterized. 7% of that is recombination loss. And at the maximum power point, when we were doing the evaluation up vertically up the IV curve, we know that it's in the ratio of 1.3 to 5.8 surface to bulk. And so we give those slices those numbers. And then finally, the last 3% takes you from the Suns-Voc curve down to the IV curve. And this is 3.5%. And this is the series resistance and the transport losses, where the recombination losses were from Suns-Voc up to the Auger limit. So that brings us to our energy loss analysis. And if you take all 350 cells, you can see the distribution of total recombination, the distribution of bulk Shockley-Reed-Hall loss. And for the J0, you see that it's steep towards the minimum, and that's the perfect implementation. And then it has a tail, which is process control variation. The RS here is very tight. And so how would you use this to make a decision if you were an engineer? Well, you have to realize that 350 cells is only 5 minutes of production data. At line speed, you'd have 86,000 cells in one day. So you could do the power loss analysis for a high bin and a low bin and see what the different losses are between those two. Or you could find the 10,000 heaviest dope cells and compare them to the 10,000 lightest dope substrates and do those kinds of things. So you have all sorts, when you get big data, you have all sorts of unintended experiments that you can really data mine with these techniques to find out how to optimize your process and your cell design. So the limitations of this analysis at IV test are that we've evaluated resistance and recombination losses. We're basically assuming that JSC is a full characterization of photo generation. So if you want to do an experiment on your AR coating, you need to do a split and put it through with 2 different kinds of cells. And for the Auger limit, we're using the measured JSC. Now, it's interesting to compare our power loss analysis with some of the others that we see in the literature. And I'm going to do a rough comparison in the next few slides to the SEGA analysis from ISFH. And I'm showing as a reference, I'll use the paper by Brendel in 2016. And what they're doing is they do a model. In this case, it's with Quokka. And they have their parameters that fit the experimental cell. And then they turn them off one at a time, leaving all the rest at the default and they find the height of each of these parameters relative to the baseline. And then you stack them up on top of each other to find the total energy loss. And what this is doing is it's evaluating them all down on this part of the curve and then just stacking them up linearly up this orange curve. And then there's this biggest bar, which is called synergy in this SEGA analysis. And from what we're doing, we can see that this is just giving a name to the discrepancy between using a linear assumption of power loss and the actual power loss when you actually run up the maximum power points of the curve. So that this was very useful to me because I found this synergy thing to be pretty mysterious, but now I recognize that it's just naming the discrepancy between the result you get when you use a linear assumption and the result you get when you do the full analysis. So what you actually have is that if you were to improve your cell from here up to here by having the J naught, then you would have a different line up vertically to the Auger curve. And as you continued to improve, you would approach the eventual Auger limit. So this is just a better mental picture. So that's kind of a good energy loss analysis at the cell level. You can also do it at the module level. And this was a very interesting experiment by Dirk Jordan at NREL. And what he had was 10 Sanyo modules, HIT modules, heterojunction modules, that had been out in the sun for 10 years. And so he could compare that to a control module, which had been in a closet for 10 years. And the IV curves are shown in blue for these two modules, and the Suns-Voc curves are shown in red. And you can see that they have degraded. Both the Suns-Voc and the IV curves have degraded. But you can actually plot the lifetime curves from these modules, and you can see that the slope changed and the offset, the intercept changed as well. So we can see that the bulk lifetime died after 10 years in the field, and the J naught, the surface passivation, doubled. So both surface passivation and bulk lifetime suffered from 10 years in the sun. The series resistance was pretty well behaved. So this is an example at the module level of degradation. And you can also do this at the field level. And this is actually my array. And you can do a Suns-Voc plot just by monitoring voltage as the sun comes up in the morning or it goes down in the evening. And this gives the part of the curve near maximum power. And then in the middle of the day, you get the voltage at one sun, 1,000 watts per meter square. And then if you turn on the maximum power tracker, you get the maximum power point so that you can evaluate the series resistance. So we have everything you need here. And it's interesting that the critical part of the Suns-Voc curve actually comes between dark and 5% of the sun. So this is the perfect illumination for getting the maximum power point on a Suns-Voc curve. So in conclusion, lifetime is extremely useful, all the way from the crystallization to the system. And it is a unifying factor in understanding every aspect of the solar cell device physics. It's been useful for more than 35 years, and we anticipate that it will be useful for 35 more years. Questions? Thank you very much.
Many thanks, Ron, for this nice explanatory and detailed presentation about the title is Carrier Recombination Lifetime, Monitoring a Critical Parameter Through the Cell Process. I may ask a simple question. Well, simple, but from the physics point of view. You underline the physics, as you are a physicist, you know, I'd like to state that. Behind reaching higher efficiency and IV curve, do you think we still have new uses of physics to reach the thermodynamical limits of the all types of cells? Do you think so?
Yes, I mean, I think the best example of that is when you have the multi-junction cells, so that you can take advantage of the high voltage available in the high energy photons. So that's one way to do it. And in silicon, of course, it's going to be kind of incremental. It will be trying to absorb more light in thinner wafers. And you have a limit, kind of a practical limit for silicon solar cells that I think will be around 27% at one sun.
Okay, many thanks. Again, we thank you for being with us from the other side of our globe, joining us and giving this nice presentation. Thank you again. Now, it is...
Can I ask a question? Is it possible?
Oh, sorry, of course.
Ron, are you with us? Ron?
Yes, I'm here.
Yeah, okay. First of all, thank you very much for accepting our invitation to give this talk. And I have a short question about this lifetime determination. It is usually difficult. I mean, in some cases, it may be difficult to distinguish, to separate different contributions to the lifetime losses, like surface recombination and bulk recombination. Can you comment on the effect of bulk recombination on the determination of the surface recombination? I mean, if you have a comparable or significant lifetime contributions from the bulk, do you still have the chance to get accurate surface lifetime determination from your technique?
So it definitely becomes more difficult. And the method that I showed here works especially well on N-type cells, because in general, the doping is lower. And so you have a high minority carrier injection, and you can separate out from the slope and the intercept. For the P-type cells, we often look at the data in a little bit different way. And that's, again, to look at the J0 close to the open circuit voltage as being most indicative of the emitter, and the J0 at the maximum power point as having additional components due to the bulk. And so when you have a big contribution due to the bulk, you can see a big difference between these two. When you have a small contribution due to the bulk, then you have a more constant J0 as a function of going from maximum power to open circuit voltage. So you're correct that it becomes much more ambiguous, the separation, but you can always tell if the bulk is dominating the characteristic, because you'll see a difference between the lifetime the J0 at open circuit and at maximum power point. So that's the strategy that we take there.
Okay, thank you.
Okay, thank you again, Ron. Now it's time for Buran Karaveli. Buran Karabeli finished his PhD at the Department of Earth System Sciences at METU, Middle East Technical University. His Master of Science thesis on nuclear versus solar issues received the METU Thesis of the Year Award in 2015. His PhD thesis on energy system algorithm on renewables received the ODTÜ Prof. Dr. Mustafa Neparlar Foundation Thesis of the Year Award in 2018. Buran has been heading the Foreign Investment Coordination Department at the Turkish Ministry of Energy and Natural Resources since August 2019. He continually working on and acting on solar energy and other renewables. Prior to his current post, he was European Union and Foreign Affairs expert at the Ministry of Industry and Technology between November 2009 to August 2019. Now it's Buran's turn. Buran will take the stage.
Good morning. I wish you and your families are well despite current circumstances. This is Abdullah Buran Karabeli from the Ministry of Energy and Natural Resources. I have been heading Foreign Investment Coordination Department for 1.5 years. It's my pleasure to make one of the opening speeches of this distinguished organization. This speech that the presentation will be accompanied covers the general outlook to the global trends, in specific to energy sector, more specifically to the electricity. Then global solar trends will follow. However, this title is mainly based on PV usage models and trends, rather than the manufacturing technologies and materials. Since the coming presentations and coming days, we will be having many information regarding manufacturing technologies and materials within this organization. I will be finalizing the speech with energy outlook and solar perspectives of Turkey in general. Checking the global agenda, we can comprehend that there are 6 magical words that have shaped the current and future dynamics of energy sector. The reports of high-level international organizations and policies leading countries made support this idea as well. It is obviously seen that we are in a transition period through more and more digitalized and electrified way of daily life. In addition to the increase in electricity demand because of the population and welfare increase, the digitalization also creates new demands for electricity. It also creates strong alternatives, how to generate electricity and meet the needs. Consequently, from heating to mobilizing, we are using more electricity by using digital devices. On the other hand, because of the sustainable development goals, especially the ones in order to combat climate change threat, the electricity generation and usage is targeted to be decarbonized as much as and as soon as possible. At this point, technology development and transfer capabilities of countries and technology readiness levels of projects play high important role. In parallel with the global trends that are affecting the energy sector highly, on electric side, we have now using flexibility words frequently. By providing flexibility of electricity generation and usage, there is no requirement for real-time generation. In other words, generation is now less dependent on the consumption time, or vice versa. Whenever and in what way we would like, we can generate or consume electricity. Creating the flexibility on both generation and consumption side is the best way to adapt to the transition period of electricity sector. Flexibility is a magical word that combines all the developments in the electricity sector. While demand-side management, together with digitalization, artificial intelligence, Internet of Things, and big data management, are important factors of demand-side flexibility, photovoltaics, together with the batteries, has utmost importance in generation side. At the end of the day, we are the prosumers. We have photovoltaic systems on our roofs and facades. We are generating electricity from there, and we are consuming the excess amount that we generate but do not consume. We can give this amount to the grid owing to the smart meters, or we can charge them within the batteries. So if we prefer to give this excess amount to the system, so we can also sell it to another person who demands this electricity with the infrastructure of blockchain and by using cryptocurrency. On the other hand, the white goods and the electric devices within the home are connecting to each other owing to the Internet of Things and artificial intelligence, so they are minimizing the energy needs. So it creates the energy efficiency. So at the end of the day, we have the system that produces electricity from the zero carbon base, and it becomes the energy efficient as much as possible. So it's the today's reality, not the fit idea for the futures. All these trends have been proven within the pandemic times we are in. At this point, International Energy Agency that announced World Energy Outlook 2020 some days ago mentions that the huge disruption caused by the coronavirus crisis has highlighted how much modern societies rely on electricity. So the reliance on electricity can be revealed as a result of the obligatory pattern changes that decreased or increased the demand. The lessons learned from the pandemic times are listed in this slide that are directly related to today's subject. Hence, nowadays we comprehended the importance of the global trends I have mentioned and the increase in social acceptance for the new transition periods. Consequently, the world is now more ready and less resistant to the digitalized world than the early 2020. That means more electrified world. By analyzing the data of 2020, World Energy Outlook 2020 mentions that there is a 5% drop in electricity demand in this year, drop in energy-related CO2 emissions by 7%, and energy investments by 18%. However, the impacts vary by fuel. The estimated falls of 8% in oil demand, 3% of natural gas demand, and 7% in coal use stand in sharp contrast to a slight rise in the contribution of renewables. So the yellow bar within this slide is presenting the renewables. So just the renewables is on the positive side with respect to investments, capacity additions, etc. On the other hand, the 2.4 gigatons of decline takes annual CO2 emissions back to where they were a decade ago. We mentioned that renewables just on the positive side, but we need to open special parentheses to solar photovoltaics, since solar photovoltaics, when compared to other renewables, has some revolution since for the last 2 decades. So this graph shows that since 2013, the distribution of the installed power renewables are on the solar side. So year by year, the share of solar within a new installed power is increasing. So the scenario of International Energy Agency shows that this trend will be carried on with an increasing slope. So we shall open a special parenthesis for solar for the upcoming years at this point. So this is also mentioned by the International Energy Agency in the report with the motto of solar becoming the new king of electricity. This report mentions that renewables grow rapidly in all scenarios, with solar at the center of this consolidation of latest generation technologies. So the new motto of this sector is solar is the new king. It can also be seen from the graphs where the agency analyzed the data and progress and made projections for the future. Both in installed power and generation projections, it's estimated that photovoltaics will be contributing the highest within all energy sources, from conventional to renewables, and will be leading sector in coming decades. So the graph is on the slide shows that since the millennia, solar period is increasing. It's in a revolutionized period. So as of 2014, the leading of solar photovoltaics within the energy sector will be proven totally. So we can easily say that we are in a PV revolution period. The main driver that paved way and shaped light for this revolution is economical rather than social and environmental, while PV investments have got substantial positive externalities with respect to environmental and social aspects. World Energy Outlook 2020 claims that with sharp cost reductions over the past decade, solar PV is consistently cheaper than new coal or gas-fired power plants in most countries, and solar projections now offer some of the lowest electricity ever seen. Not in the technology development, but from the implementation model, side that affects the technology development as well. Photovoltaics is now popularly used with the works of digitalization, roofs and facades of the building for the near zero emission buildings. Relatively, floating photovoltaics has also utmost importance in these days in Terra. By the way, rooftop facade and floating models exempt the investments from the land usage because they are using the land that was already used by some activities. So digitalization creates an opportunity to easy operational maintenance and to determine the easy feasibilities. So the satellite data are one of the opportunities by the digitalization, the drones for the operational maintenance, remote sensing and control, the cloud computing for the data, the satellite forecasting, and digital field workers are all the opportunities for the easy operational maintenance of solar photovoltaic systems. So digitalization has both effects. It increases the electricity needs and it increases the devices that use electricity. On the other hand, it also eases the operational maintenance of photovoltaic systems and the data management of these systems. So for the floating photovoltaics, it's also very attractive in these days. So the system limits the algae production for the reservoirs that are installed, and they limits the evaporation of the water. So it is demanded for the man-made reservoirs, but the algae production is not demanded by the natural reservoirs. So I put this slide since they mentioned that it's good opportunity to install photovoltaic systems to the man-made reservoirs. So when we compare the cost, if you install a system to land and if you install a system for the reservoirs, then the price difference is around 30% according to the World Bank study. But if we take the land cost into account, then this 30% is melted down. On the other hand, because of the efficiency increase for the cooling effect of water, the electricity production increased around 15% for the floating photovoltaics. Another interesting study by the World Bank says that the required area for floating photovoltaics to match the dam's hydroelectric capacity is 3% of the reservoir site. For instance, Atatürk hydroelectric power plant is the biggest in Turkey. Its reservoir size is 820 kilometers square, and its installed power is 2.4 gigawatts. So if we would like to have 2.4 gigawatts of installed power at this region, we just need to use 3% of total reservoir area. So the generation side, Atatürk generation capacity is 8.1 terawatt hours per year. That means 1 gigawatt of system generates around 3.4 gigawatt hours. So it means that it's the twofold of photovoltaic systems. That means we just need 6% of reservoir size to have the same generation. So it shows the advantageous ways of this floating photovoltaics. So we easily see that in the coming period we will be using these floating rooftop and facades and digitalization works too much. Coming to Turkey from the global aspect, Turkey's energy sector has been driven by three major characteristics. These are growing energy demand because of the population and welfare increase and import dependency. Turkey's natural gas demand in 2019 was 45 Pcm and 99% of this demand was imported. It's also same for oil, 91% of oil was imported as well. On the other hand, in order to solve the problem of this challenge, Turkey has huge renewable sources from hydro to wind to solar to geothermals. Furthermore, Turkey is also directly connected to the world, starting from Europe. That means all the infrastructure, the technical activities and the legislation should be in compliance with the Europe and the world as well. So with these drivers, Turkey has had its own circumstantial energy transition phases. In the first phase, between 2001 and 2016, Turkey introduced radical reforms and restructuring in the energy sector. In the second phase, starting from 2017, which is mainly inspired by the national energy and mining policy strategy, there are three pillars. These three pillars are reinforcement of security of supply, localization to renewables and domestic sources, enhancement of predictability in the market. So all the policies after this 2017 are affected by these three pillars, and they serve for these three pillars. So maximum utilization of photovoltaics is also one of the main objectives cross-cutting these pillars. Once we check the Turkish electricity output with main parameters, Turkey has got 94 gigawatts of cumulative installed power, and more than half of it is from renewables. If we divide this renewable source into the sources, like we have 30 gigawatts of hydro, 8.3 gigawatts of wind, 6.45 gigawatts of solar, 1.6 gigawatts of geothermal, and 1.4 gigawatts of biomass. So for the generation side, a new generation of 2019 was 304 terawatt hours, and as of the end of October, this year's generation is 253 terawatt hours. So it shows that at the end of the year, we will be having similar amounts that we generate in 2019. So 45% of this year's generation is from the renewables. So it increases day by day. So some days ago, the minister announced that for the first 9 months of 2020, 98% of the investments in Turkey, the energy investments in Turkey, is from the renewables. That means that in the coming period, we will be seeing more renewables than the conventionals. So the country's targets for 2027 are these. The first one is to have 2 or 3 share of its generation from the renewables and domestic sources. The second one is having 8 gigawatts more wind by 2027. And the third one is like having 7 gigawatts more solar by 2027. Testing the Turkish PV market dynamics. 3 main models to develop the market are the ground-mounted utility-scale investment, as is applied in majority now, the promising rooftop and facades, and the sui generis feed-in pyramid model, namely renewable zone tenders. Almost all the currently installed power is ground-mounted power plants, whose installed power vary around 1 megawatts. So the legislation says that till last year, the legislation said that if you are going to install the system for the self-consumption and the installed power if is lower than 1 megawatts, then you are exempt from the licensing period. If not, then you need to have a license. That's why the majority of the power plants in Turkey has the installed power around 1 megawatts. This 1 megawatt threshold is increased to 5 megawatts with the presidential decree in 2019. For the next period, we see that the trend is for rooftop photovoltaics. There are many applications for the consumers, for the industrial activities to install the photovoltaics to their roofs. So at the end of the day, we have 6.45 gigawatts of installed power as of 2020. This installed power is photovoltaics. Then this corresponds to around 7% of total installed power of Turkey. It was 94 gigawatts. So the generation till the end of October 2020 is around 10 gigaterawatt hours, and it's the 4% of total country's generation. So like I said, the recent years accelerated effect is from the sui generis model, that's renewable zone tenders. We have 2 for wind and 1 for solar until now. They are all successfully completed tenders. And the next one will be solar PV in the beginning of next year. So as a part and requisite of a renewable zone tender for solar that was in 2017, solar PV module manufacturing facility, that's the first and only integrated manufacturing facility in Europe and Middle East, has become operational in Ankara as of August 2020. Hence, this facility is now able to manufacture PV modules starting from the raw materials and covering full manufacturing steps such as ingot, wafer, cell, and module production. Like I mentioned, the rules of mixed next renewable zone tender for solar has been announced. By having total 1 gigawatt of installed capacity, we will be holding 74 competitions in 36 provinces in capacities between 10 to 20 megawatts. For the first one, the government declared the location and announced that I will be having one tender for 1 gigawatts, and it has some requisites like installation of manufacturing facility, establishment of R&D center. But for the second one, the government is now applying 74 competitions. That's why this tendering period is called as mini renewable zone tendering periods. On the other hand, by learning, by doing process, the country has now major legislation regarding photovoltaics, and we have incentives. Then the main incentive is called as YEKMEL in Turkey. It's a renewable energy support mechanism. So for the first version, the support mechanism is expected to end at the end of 2020. So the mechanism said that if we install the photovoltaic system till the end of 2020, I will be purchasing your electricity for 10 years with a 13.3 kilowatt hour, or dollar cent per kilowatt hour, but it's extended to the mid 2021. So now, if you install a system in Turkey till the middle of 2021, I mean the end of June 2021, so you will be having this incentive till 2030. So post mid 2021 period is determined now in the Turkish National Assembly. The ministry has drafted the legislation regarding the new mechanism for the incentives. So it's now discussed in the Turkish National Assembly. I think in the coming days, we will be having our new mechanism. For the last sentences for the Turkish PV market, the Stantec company has made a research regarding the Turkish manufacturing capacity of photovoltaics. So they determined that there are 16 manufacturers, and the total annual production capacity of this 5.6 gigawatts, and all the capacity is for the crystalline silicon systems, technologies, and according to the report, there are no thin film manufacturing facilities. But this number, that 5.6 gigawatts, is not including the PV manufacturing facility that was operationalized as of August 2020 in Ankara. So if we add this, and we are now having around 6.2 gigawatts of new manufacturing capacity. The last but not the least, as a department I have been heading, we developed a strategic framework covering all the world trends and country priorities and skills in order to channelize project programming processes for the international funds, because our department are responsible to develop projects and to find the appropriate funds from the international organizations. So the strategic priorities of our framework are low carbon solutions in the energy system, connectivity and integration of the energy sector, and technology transfer and development in this sector. So the technical priorities that you've seen is digitalization in the distribution scale and smart and green infrastructure in the big scale like transmission. So photovoltaics is at the heart of this strategic framework, since it's also in my heart. So thank you for your listening. We're a fruitful and beneficial organization. If you have questions, then we can elaborate the issues in the question and answer session. Have a nice day.
Many thanks for this nice and fully covering presentation. What's going on in Turkey, about what's going on in Turkey in terms of solar PV. So it was very explanatory, as I said, and fully covering presentation. I may ask a question, Buran, to you, because it seems to me it's quite important. Now, the solar PV will increase in Turkey, and we should believe that it will saturate somewhere at some point within some years. Can you give any guess about that saturation point and the amount of gigawatts that will be installed in Turkey in terms of solar PV?
So, thank you, Bülent Hocam. Initially, very sorry for the rustle. I don't know the reason why there is a rustle, because all the devices are new that I used, that I recorded, but there is a rustle. Sorry for that. I hope that everything is understood. If not, please inform me, then I make this presentation again for you. So,
yeah, in fact, you're right. You were right, but we can hear anyway. So the presentations and the actually that conference will be is taken and it will be announced. It will be given in our website. No problem. It was okay. It's nice.
Thank you for your question. So the sector, the technological development decides the threshold that we need to reach and stop there. So we saw that when there is a legislation and good incentives, then the sector turns to the photovoltaic side. So as of 2015, once the incentive is determined and the legislation is finalized, then we saw sharp increase in installed power. So once the government decides to stop the installation of the 1 megawatt projects under unlicensing period, then the incentives slowed. So that means the technological developments and the incentives and the legislations and the sides of the policymakers will decide this threshold. So the technology is saying that you may have in the coming years all the installed power from the solar PV, because the main obstacle against solar PV was the economical side. So all the reports are now saying that solar is the one of the cheapest source, and in the coming years it will be the cheapest. So technology have things to do. The legislations is there. The policymakers are now very conscious about the photovoltaics. So I think the maximum utilization from the photovoltaics will be, but I cannot now say the exact number for this.
Okay. Thank you for these explanations about the threshold and about how it will go. It's going and it will go. Now, thank you again, Buran. Our next speaker is Fırat. Fırat S is with us now. Fırat S completed Bachelor of Science and Master of Science degrees at Physics Department of Middle East Technical University. He received his PhD degree on micro and nanotechnology in 2016. He worked as a researcher in UNAM and worked on development of crystalline silicon solar cells between 2009 to 2019 as the head of crystalline silicon group. Between 2016 to 2019, he also worked in UNAM photovoltaic line, what we call GPVL, as pilot line manager on development of PERC-type silicon solar cells. His main research interests have been industrial crystalline silicon solar cells, technology, and metal-assisted texturing for black silicon solar cell fabrication. In 2019, he joined Kalyon PV company as cell module integration manager, and from 2020 till now, he's working as the research and development manager for Kalyon PV integrated factory. Kalyon is our gold sponsor of this conference, just to remind. Now it's Fırat's turn, and Fırat will take the stage.
Thank you very much, Bülent Hocam. Can you hear me?
Yeah, we can hear you.
Okay, just to check, because I'm going to go live. I don't have the recorded presentation.
Yeah, okay. Thank you, Fırat. And just I remind you the time. Maybe you know it already, but And the time is, as you may guess, is up to 10:50. Okay.
Yes, Hocam, thank you very much. In fact, since we are a new factory and a new research lab, in fact, I don't have too much to say in terms of scientific content, so it will be just showing our factory and showing our research interests. So
this will be okay. This will be interesting. Okay, thank you. We wait for that.
So it will be a fast presentation. Thank you very much for inviting me for this talk. It's very honorable to be here in the same talk with these speakers, especially Ron Sinton. It's a coincidence because 10 years ago, when I just started at UNAM, the first tool that I asked Professor Raj Turan, to purchase was the Sinton WCT lifetime tester and Suns-Voc tester. So it was the first tool that we purchased for our laboratory at that time. And 10 years later, I am again in another research lab, and we are still again establishing a new laboratory. And the first machine, the first tool that we purchased is again a Sinton WCT lifetime tester, this time with a temperature controlled measurement chuck. So I hope it brings luck again to all of us, and it really helps all the industry. I know that it helps industry to develop a lot. Let me start my presentation. I will be talking about our integrated PV manufacturing factory and some of our R&D activities that just started. As I said, so my outline, I will talk about the YECA project and Kalyon PV, and then our technology and production figures, just some small figures about our production and about our research and development department. So what is YECA? I can start with YECA project. As we mentioned, it stands for Renewable Energy Resource Area. It's a governmental strategic project, and it's a bidding, and its aim is the use of renewable resources in a functional, efficient manner in Turkey, and also support and transfer of production know-how for renewable energy. And in this case, this renewable energy production know-how stands for photovoltaic technology, crystalline silicon photovoltaics technology. And in order to fulfill these requirements of this YECA project, Kalyon YECA Karapınar solar power plant is being established in Konya Karapınar. It's a desert area in south of Turkey with a 20 million meter squares of area. And there, as Kalyon PV, we are going to install 1,000 megawatts AC of power plant, silicon solar cell power plant. And there we will be using 3.3 million of our modules that we produced in our factory. And the main energy output of the solar power plant is expected to be 2,600 gigawatt hours per year. And in the end of its production, when it's in maximum capacity energy production, in 1 year, it will give the 20% of Turkey's solar energy production. So it will be 1/5 of Turkey's solar energy production will be supplied by this power station. So it's a very big project for Kalyon PV and also for Turkey. And in this power plant, we are going to be using bifacial and tracker technologies together, so that we are getting very high energy yield throughout the day by tracking the sun and also using the albedo from the ground. And as I said, this is a governmental strategy, and it supports and transfers the production of know-how from renewable energy, which means that there are some rules to be done. And the biggest one is that modules that are manufactured shall start from polysilicon. So you cannot directly purchase modules and put it in the power plant, or you cannot purchase cells and make modules. But you have to start from polysilicon. And in order to fulfill this requirement, we established our Kalyon PV Solar Technologies factory in Ankara. We have a 100,000 square meter of closed area, factory area under one roof. And we have 500 megawatts of production capacity per year. We produce 500 megawatts modules per year, and in the mid of 2021, we will be having an additional 500 megawatts of capacity. Now we started to establish these new lines in our factory. And we have the integrated factory concepts. So ingot, wafer, cell, and module lines are all under the same roof, are being produced under the same roof. And this allows us to produce our cells or modules with a 75% domestic locality ratio. So it supports domestic production, and we are continuously trying to enhance this ratio. We have 1,400 personnel right now, and with the extension, we will be reaching 2,100 personnel. And we have under the same roof, we also have an R&D center of 2,500 meters square, where we are going to develop our technology to supply technology to our factory. And I can say production started in August 2020. So we are a new factory. In fact, quickly the module factory ramped up. Now it's close to full production. Ingot factory is also close to full production capacity right now. Wafer and cell factories around 75% production capacity, and by the end of 2020, we are planning to reach full capacity production, 500 megawatt production. And all cells that start from ingot are laminated and modules are made, and they are sent to Karapınar. And in Karapınar, we also started to sell electricity with a small volume. And little about our technology. We have the ingot factory. We have 72 pullers in our factory, and we have more than 500 megawatts of capacity. And we are using we are using a Czochralski growth method to grow our monocrystalline ingots. The ingots are boron doped P-type, and each of them are around 4 meters long and around 350 to 400 kilograms. And in our wafer factory, we are using diamond wire sewing, and we are using G1 standard 58.75 millimeter full square wafers, and our wafer thickness is 180 microns. In our cell factory, we are using monoperk technology. We are with bifacial property, so both sides are contacted with fingers, and we are having 22. Our starting efficiency target was 21.8, but now within such a small time, we reached 22% average efficiency from our production line, and some efficiencies up to 22.5 are being reached in the other side of the limit. And our cells give 70% bifaciality. And in our module factory, we use our cells to produce modules. We are using 72 half-cut cells, so 144 half-cut pieces are used. That helps to reduce the high current due to this large sample area, and cell to module losses are decreased. We are using glass frameless bifacial modules, so we can use electricity coming from the albedo, and our module power average is 400 watts right now, and our bifaciality is around greater than 70% for our modules. And when we come to our research and development department, we are legally established at 1st of September 2020, but until that time we had been in some preparation period. Due to COVID, we had some stops, but we tried to make as much as we can do. As I said, we have 2,500 meters square R&D closed area with offices and one test and characterization laboratory and one clean room. The clean room is being established right now, and test laboratory we are starting to purchase our tools. And we have our team has the average age we can see as a 29, which is young and very enthusiastic on developing new technologies. When you see the education level, you can see that 60% of has bachelor degrees, and 15% of Master of Science degrees, and 10% of PhDs are working with us, and we have 15% of technicians in our laboratories and R&D centers. And this is the gender distribution: 35 female and 65 male researchers are working in our research center. And we have 5 years R&D strategic plans as a portfolio of our R&D center. I will give some more details about them. The first is the cell and module efficiency improvement strategic plan, where we are working on cell, about device and materials optimization, and modules on BOM development and CTM optimization to increase the efficiency of our cells and modules and decrease the costs. And another one is the semiconductor production process techniques, is in the another 5 years R&D strategic plan of our R&D center. And here we are mainly focused on N-type technologies, especially IBC and TOPCon, and also in crystal growth techniques. We are working on quasimono and increased wafer sizes in our strategy and decreased wafer thickness. Also, we will be working on gallium and phosphorus doped ingot production. Phosphorus doped goes to N-type technologies, and gallium doped will be helping to reduce light index degradation of our P-type solar cells. We are also working on automation and Industry 4.0. In this concept, we are mainly interested in smart factory concept, and we have an MES system, and we are trying to adapt the physical wafer tracking to this system, just to get as much as data from each wafer as possible. And also we are interested in artificial intelligence and machine learning on process development. We believe that these techniques are going to take over within time. And also we are very much interested in flexible factory concept, where you can produce P-type and N-type solar cells under the same equipment structure. We are also working on energy storage systems. We are especially working on chemical storage system, and main idea is peak shaving and battery management systems are to be studied in our R&D center. And lastly, energy production and advanced characterization. Here we are mainly focused on life cycle energy yield assessments of industrial modules, or the modules that are outcome of our R&D projects, and also levelized cost of electricity calculation, advanced characterization of PV devices, and photovoltaics and agrovoltaics are mainly in our energy production advanced characterization research program. I will give some examples of the projects that are going on right now in our project, not all of them, but some highlights. First one is FlexFab2, that we are working together with IST Constance, RCT Solutions, and VDMA. Here we are working on, as I said, flexible factory concept for P-type and N-type cell processing in the same factory. And we are working on N-type ingot growth, development of N-type IBC cells, decreasing the wafer thickness, and PERC cell development, both N-type and P-type. In this project, we are an associated supporting partner to IST Constance, and we are going to develop a factory model that can process P-type and N-type solar cells under the same roof. Another research program is energy production projects that we are doing together with Günam and Hasan Kalyoncu University. In Ankara factory on the ground, we are going to be testing different types of modules in our test site. Also in Ankara factory rooftop, we are going to have some test facility to test rooftop modules, and also some rooftop tracking systems, which is really interesting. Also in Karapınar, in order to see the harsh conditions in Karapınar, there we are going to have a test site. Even though the Karapınar as a whole is a large test site, this will have a more controlled environment, especially the desert, and the soiling is a very big problem there, and we are trying to solve it through some cleaning robot development, but we are open to any suggestions from all researchers. And also in Gaziantep, where our university is located, we are going to place a module test site, so we will have a big resolution throughout Turkey. Also in other universities, we are trying to make this and have a good resolution to get the solar assessment, yield assessment throughout Turkey. Energy storage, again, we are working with RCT solutions and we are in contact with Aspilsan and Endam. Endam is from, again, Metro. The main thing here is we are very interested in peak shaving because especially in our power plant and in our future power plants, the peak energy that cannot be used at the highest energy generation times can be stored in the batteries, and in times where there is less sun, where you cannot use this energy, you cannot produce this energy, you can use your energy storage systems so that the total system cost is going down and you are producing more energy than expected. And also, especially we are interested in lithium-ion and sodium-ion batteries, which can be possible candidates for such big utility scale battery systems. We are not only working on novel on crystalline silicon, but also we are open to novel concepts. Around 20% of our budget is allocated for basic research and novel concepts. We have an Aranet solar that just passed on perovskite module development, having a lead-free and degradation-free nature. We are going to develop BS Callium PV will be on the module fabrication in the industrial environment of this perovskite cells, and we will increase we are going to try to increase the TRL level from 3 to 6 throughout this project for modulation, encapsulation of perovskite cells. And in summary of our R&D centers projects, when we separate them by funding, we have 2 projects up to now funded by external funding, and 2 projects have been submitted to international agencies. And in terms of self-funding, we have 19 projects ongoing and 8 projects are being preparation. When I say self-funding, it's completely funded by the company itself. And when we take projects by team, I can say that we have 3 projects on novel technologies right now going on. We have 2 points on localization. When I say localization, I mean developing the domestic market for raw materials or systems that can be sold in Turkey rather than purchasing the goods from abroad, because especially in times like this where you have international crises like Corona, we have seen that we must be as independent as possible to have this freedom in energy generation. And also, of course, optimization development. 13 of our projects are devoted to optimization development of our ingots, wafer cells, modules, and factory itself. And also recycling and zero waste. We are also working on recycling of the sources that we are using, and also trying to be as nature friendly as possible. And we have 3 projects on recycling and zero waste. And up to now, our collaborations in the world, this is not a fully completed map of the world, but in very little time, we had chance to make collaborations and make project proposals with different countries in the world, starting from China up to UK. And also in Turkey, we are also trying to make as much collaboration as possible in order to share ideas and share knowledge that are generated from R&D projects. And we would like to make as much collaboration as possible. And I would like to indicate that you are always welcome to visit us and to make project proposals to work together. With this, I would like to thank you all, and if you have any questions, I am happy to answer.
Okay, many thanks, Fırat, for this nice presentation and introduction to Callium PV from the RD part, in fact. So I have a question about how in Callium PV is going for the future. For the time, to the best of my knowledge, for Karapınar, your factory will be working for you. for that 1 gigawatt. But I should think that okay, in the RD part, you are collaborating with other countries, with other nations, and also in Turkey, you are collaborating with different scientific groups in the RD part. But what about on the market? On the market, Kalyon has any projection to an international level to share the market for the PV, for solar PV, or for the other energy projects that you mentioned, the RD energy projects? That's the question.
Thank you, Hocam. As you said, for the coming 2.5 years, our ingot to module production lines will be working for Karapınar factory, because we have to fill 1.3 gigawatts of DC power there. But while doing this, our management decided to increase our capacity 500 megawatts more, so that we will be having additional 500 megawatts production for the Turkish markets. And this is mainly we are mainly focused on again utility scale systems, but also rooftop systems are also in our strategy, and therefore we are not only working on directly on photovoltaics, but hybrid systems that come with a complete solution. These are in our future product strategies, and we would like to be one of the first steps of this production coming out from China and going through Europe and the West. And I think we are the first step about this 10 gigawatts of solar production aim of West out of China. That's all I can say.
Okay, thanks. Thanks for these explanations. Actually, for all of the keynote speakers, or for all of the participants, the questions may continue, and we will send these questions later to the speakers and to the participants. Now, this is the end of the opening session, and with Fırat's speech, we finished the first part. And let me first give information about the next section. Next section is about advanced crystalline silicon technologies. It's the first part. Rashid will be chairing it. At 11, it will start at 11, and it will go up to 13:10. So we have now break, and we are waiting all of you in this next section to join and to see the presentations and to see what is going on solar PV in Turkey and on an international level. Okay, many thanks for all of you who joined this session.